As you may already know, atmospheric pressure drops as you go higher up in the atmosphere. What we're going to do is to derive a function P of z, which will give us atmospheric pressure at a given altitude z, so that we can really see how it is changing as the altitude increases. But let me first draw a column of air and a z-axis. I will do my column of air. Looks something like this. Okay. Okay, and our z-axis. Altitude z. Before tackling this problem, we'll first need an hypothesis. The static fluid hypothesis. What we'll say is that our column of air will stay at rest. What does that mean? That means that if I take any infinitely small slice of air of this column, and this is an infinitely small slice of this column of air, it won't move over time. Or if we apply Newton's second law to it, that will mean that the sum of the forces exerted on this infinitely small slice is equal to 0. Let's summarize what are the forces exerted on any of those slices. Let's take this one, for example, which is at altitude z. We already know that this slice is experiencing the weight of the column of air above it over its upper surface. But since it is at rest, it must also experience the same pressure on its below surface. This pressure is what we call the atmospheric pressure at z, or P of z. Now let's do something quite interesting. Let's draw another slice delta z away from the first one we drew. Maybe it will look something like this. So this slice will be at altitude z plus delta z. And it will experience a pressure of P of z plus delta z. There we are, our first slice was experiencing a pressure of P of z, which really was the weight of the column of air above it. And here our second slice, which is delta z away from the first one, will experience the weight of this above column of air. But if we think about it, we can derive a relationship between P of z plus delta z and P of z. Indeed, the pressure at altitude z will be equal to the pressure at altitude z plus delta z plus the weight of this cylinder of air divided by the surface of this slice, this infinitely small slice of air. So maybe, just maybe, we can write the following relationship. P of z is equal to P of z plus delta z. So the pressure, the atmospheric pressure at z is equal to the atmospheric pressure at z plus delta z plus the weight of this cylinder of air. So what it will be? It will be the surface of this cylinder of air, so S, times the height of this cylinder of air, which is really delta z, multiplied by the density of air. We'll write it this way, times g. So this is the weight of this cylinder of air, but we want the pressure, so we'll divide by the surface S. But the question is, can we really draw an equal sign here? If we were to draw an equal sign, we would suppose that the air density is constant, whatever the altitude is. But is it really the case? No, it is definitely not the case, and we can already guess why. It is because the air density at a given altitude will depend on the pressure at this given altitude. In order to understand this, you really just have to imagine a box full of air molecules. What will happen in this box is that the air molecules at the bottom will actually be pushed together because of the weight of the air molecules above them. So the air density at the bottom, we'll write it this way, will actually be greater than the air density at the top. So that is why the air density depends on the altitude and is not constant. Now, imagine our delta Z is small. Well, in that case, we can say that the air density in this small cylinder will stay roughly constant. And that's key. Because now we can rewrite our relationship so that it becomes true. And we can really say that the pressure at Z will be approximately equal to the pressure at Z plus delta Z plus the weight, the surface of the cylinder times delta Z times the air density at Z times G divided by S. So what we said here is that we considered the air density to be roughly constant over this interval delta Z. And we used the value of the air density at Z over this whole interval. So this relationship is true, but this one is not. Now, what's really fascinating about this relationship is that it will get more and more accurate as delta Z goes to 0. Indeed, as delta Z is getting smaller and smaller, we will consider the air density to be constant over a smaller interval delta Z. We will block the value of the air density over a smaller interval. That is why our relationship will get more and more accurate. Now, maybe we can simplify this relationship. We can say that the pressure at Z minus the pressure at Z plus delta Z will be approximately equal to the surface times delta Z times the air density at Z times G divided by S. So we can get rid of the surface. We can divide both sides by delta Z so that we will get that the pressure at Z minus the pressure at Z plus delta Z divided by delta Z will be approximately equal to the air density at Z times G. What if we multiply both sides by -1? We will get that the pressure at Z plus delta Z minus the pressure at Z divided by delta Z will be approximately equal to minus the air density at Z times j. There is something really interesting going on here, because previously I told you that as delta z is going to 0, this relationship will become more and more accurate. So let's just take the limit as delta z goes to 0 of both sides of this equality. We will get that the limit as delta z goes to 0 of the pressure at z plus delta z minus the pressure at z divided by delta z will be this time equal. Now it is an equal sign because delta z is going to 0. So it will be equal to the limit as delta z goes to 0 of minus the air density at z times j. But wait, there is something going on here. This is just the derivative of the function p of z. So we get the following relationship. We get that the derivative of the function p of z with respect to z is equal to the limit as delta z goes to 0 of minus the air density at z times j. So this does not depend on delta z. So this is equal to minus the air density at z times j. So we are starting to get more information about our function p of z. But maybe we can even go a little further using the gas law. What do I mean by that? Coming back to our small cylinder of air, we can say that if delta z is small enough, infinitely small, we can say that the density of air at z is equal to the mass of the cylinder divided by the volume of the cylinder. But we know that the mass of this cylinder is equal to the number of moles of air molecules in this cylinder times the mass of 1 mole of air molecules divided by Vc. But the ideal gas law states that the pressure at Z times the volume of the cylinder will be equal to the number of moles of air molecules in this cylinder times the constant air times the temperature at Z. So again, this is true because delta Z is infinitely small. For the sake of simplicity, we will consider that the temperature does not depend on the altitude Z. It will stay constant. So if we combine those two relationships, we can say that the pressure at Z times the mass of 1 mole of air molecules divided by air R times T will be equal to the air density at Z. So now we can write a new relationship. We can write that the derivative of P of Z will be equal to minus P of Z times M sub A divided by R times T and times J. So this is just a differential equation. And if we solve this differential equation, we get that the function P of Z is equal to P sub 0, which is the atmospheric pressure at ground level, times the exponential of minus S sub A, M sub A times J divided by RT times Z. So if we graph this function P of Z, let me just draw the axis Z, axis P of Z. We will start at the atmospheric pressure P sub 0, which is the atmospheric pressure at ground level. And starting from here, the atmospheric pressure will decrease exponentially as the altitude increases.